All right, well, this is a lot of boxes to check for one quiz, but I don't think it's that hard to think about. So let's go through this. In a clique, each node is connected to each of the other nodes, so the degree is linear in the number of nodes. But think about path lengths. Every node is connected to every other node, so the paths you can always get directly from one node to any other node. Very, very small world, but it's a small world because everybody knows everybody. And we know that that's not what our world is like. Though if you go to a small private school, you may have exhibited exactly this kind of effect. All right, next let's think about a ring. What happens in a ring? Well, the degree in a ring is always 2. All the nodes have degree 2, so it's a constant degree. But what about a path length? What's the longest path length in a ring? Well, some of the nodes are really nearby, but some of them you have to go all the way to the other side to get to them, and that could be as big as the number of nodes n divided by 2 because it's the opposite side. After you get further and further and further, you start to get closer again. So the path length is actually linear in this case. Balanced trees are really interesting. So the degree here, well, a node might have a parent and 2 children. This is a balanced binary tree in particular. The root node has a degree of 2, and all the leaves have a degree of 1. So it's never more than 3, no matter how many nodes are in the graph. So the degree is constant. But let's look at the path length. Any node can get to any other node by going up to the root and then back down to the other node you want to get to. Getting up to the root takes logarithmically many steps, and then going back down also takes logarithmically many steps. So it's like 2 log n. So that's actually a pretty short path for a big graph. It's not that many hops you have to make to get to where you're going. All right, finally, let's look at our friend the hypercube. In a hypercube, each node is numbered with log n bits, and it's connected to all of the other nodes in the network that have names that differ by at most 1 bit. There's at most logarithmically many of those. So each node in a hypercube is connected to log n other nodes. The degree is big theta of log n. Now what about path length? If I want to get from one node to any other node, what do I need to do? So we didn't talk about this before, but it's actually kind of neat. So let's imagine we want to get from some node, and here's its label, 010, to some other node, and here's its label, 111. We know in one hop, we can go from 010 to 110, and then in one more hop, we can go from 110 to 111. In fact, to go from any node in a hypercube to any other node in a hypercube, all you have to do is go through the bit positions one at a time and traverse the corresponding edge if the source and the target differ in that bit position. So in most log n hops, we can go from any position in this hypercube to any other position. So again, pretty short paths.